Formula Student Design Reveal. My name is Oskar Ling. I'm a part of the Business and Marketing subgroup, and I'm also the head of sponsorship for the CFS team. We'll begin this event with a tribute video for last year's car Svea, which won Formula Student Germany's Driverless Cup last year. Then we'll have some words from our team captain, Albin Bachterbo. Then we'll have the design reveal. And afterwards, each of the subgroups will present their part of the design. I want to take this opportunity as the head of sponsorship to thank all of our amazing sponsors for making yet another season of CFS come to life. So first and foremost, on behalf of the whole CFS team, I would like to thank our amazing VIP sponsors, and that is of course Volvo, Arrows, Astrid, and Chalmers. I'd also like to thank our amazing gold sponsors, Hexagon, Novatel, Ergonomics, SKF, Vårgårda Flygplats, EMC Services, and Chalmers University of Technologies, area of advanced transport. I also want to thank our silver sponsors, that is A-Free, CPAC Systems, SSAB, Wiretronic, and Sensoric Solutions, Eder Medeso, Sundström, Toffee X, Ansys, JSys, and Beta Simulation Solutions. Last but not least, I would like to thank our bronze sponsors. So once again, on behalf of the whole CFS team, thank you so much for making this possible. I also want to dedicate a special mention to my subgroup, Business and Marketing team. We will not be presenting anything today because we're not involved in the technical design, but we're responsible for other things such as the static events, livery, merch, business, marketing, social media, and events like these. Now, let's play the video thanking our last year's car, Svea.
Thank you, Oscar, for a great introduction, and thank you, Svea, for an incredible year. My name is Albin, and I'm the team captain of Chalmers Formula Student 2026. Before we get into this year's team and car, I'd like to briefly recap last year's season. In 2025, we managed to secure a first place in the Formula Student Germany Driverless Cup, as well as a second place in the Formula Student Czech Republic Driverless Cup. This ultimately resulted in us ranking the highest amongst all driverless teams in the world. In addition to this, we also managed to complete more than 650 kilometers of testing. This sets a high bar for 2026 and motivates us to push even further. And the amazing people that will make this happen are my teammates in CFS 2026. Let's give them a big round of applause. Our team consists of 87 students divided into 8 different subgroups. And you're going to hear more from each of them today as they present what's been developed and improved for this year's car. In addition to this, we have 3 key roles within the team. Project managers, they are returning team members supporting the overall development of our car. We have project engineers who make up the majority of our team and are responsible for actually designing and building the car. And we also have junior engineers who are bachelor students contributing across all areas of development. This year's team have people from 12 different nations with diverse academic backgrounds. This diversity strengthens our problem solving and our innovation abilities. Our project follows a structured timeline. Recruiting begins in September, followed immediately by the design phase. This is when we model the entire car in CAD and perform the majority of our simulations and calculations. In January, we transition into the manufacturing stage. During this time, we reorganize into manufacturing subgroups, such as metals or composites. And also, we actually manufacture 95% of our car in-house here at Chalmers. Leading up to the competition season, we conduct extensive testing and validation to ensure that all our systems work as intended. A lot of time and energy goes into fine-tuning components, such as the control system or the suspension. Finally, all our work throughout the year ultimately leads to the competitions. This is when everything is put to the test and our performance is measured against the best teams in the world. This year, we will participate in the Formula Student Germany and Formula Student Czech Republic competitions. These are 2 competitions with very high standards and incredibly high competitiveness. And now that you've heard a bit more about our... Let's shift our focus and allow me to introduce the car of Chalmers Formula Student 2026.
So hello everyone, my name is Philip and I'll be doing the presentation for mechanical powertrain. But first of all, what includes the mechanical powertrain and its CAD? Well, it includes the T-sack, the inverter and its motor together with its cooling system. So one of the things we have changed this year is the gearbox. This year we have redesigned it a little bit with the result of being able to reduce the total weight of it by 23%. Then we have the motors. this year we're utilizing the same stators, but we have redesigned the motors. With this improvement, we have been able to increase the power by 48%, and we've been able to increase the torque by 48%. And with all of this, we've been able to reduce the actual total loss of it by 19%. Then what about the motor cooling? Well, the motor cooling this year has been changed a little bit, but uses the same foundation as last year. One of the major things is the new topology optimized internal fins for the motor. With this improvement or this utilization of this new motor fin, we've been able to reduce the peak motor temperature by 5 degrees and been able to reduce the average temperature of the motor by 3.5%. Now, last but not least for mechanical powertrain is a TSAC, the tractive system accumulator container, which includes both the battery and the relay box. And this year we have redesigned it from the ground up. A change in cell selection has allowed us to optimize the TSAC and relocate the relay box from the front of it to the rear of it, helping with mass distribution and helping with packing efficiency of the TSAC, something that will come to enhance the car's balance and stability on the track. Now, what about the cell segments themselves in the TSAC? Well, we have redesigned them as well with reduced complexity, and we're utilizing a new innovative design layout. Now, what has all of this resulted in? Well, it has resulted in a 25% reduction in total TSAC mass and an increase in energy density by 54% compared to CFS 2025, showing a massive development leap in TSAC design for Chalmers Formula Student. And with that said, I would like to thank you very much for listening to Mechanical Powertrain. Now I would like to invite Lucas from Electronics.
Thank you, Philip. My name is Lucas, and I'm part of the electronics subgroup. And on the image here, you can see the rest of my fantastic team. The electronics subgroup can be divided into 3 main areas of responsibility. We have the tractive system hardware, which mainly concerns the electronics in the powertrain, including things as the inverter and battery. We have the low voltage hardware, which mainly concerns the electronics outside of the powertrain, such as the harness and our electrical nodes in the car. Lastly, we have the embedded software, which handles the communication and coordination between the hardware in the car, for example, within our battery management system. Altogether, in all these 3 areas, we handle things like power distribution, communication, safety systems, and much, much more. Now I would like to take you a little bit into the workflow of the electronics subgroup. So every season starts with the pre-study, where we review the old car and start evaluating new concepts. This period involves a lot of data sheet reading, doing accuracy and thermal calculations, simulations, and much more. Once we've decided on a concept, we move on to make schematics of the electrical system. When that's done, we move to the physical layout, where we actually design the physical electronic systems that are going to go into the car. Once that is done, we start manufacturing, where we solder, crimp, and manufacture the entire hardware system. When we're done with manufacturing, we start testing. First, we test individual functionalities of our electrical system. Then we move to test entire PCBs, and eventually we integrate it all into the improvements. For example, we have a new in-house battery voltage measurement solution that allows us to read the total battery voltage at a much higher frequency. We have reduced complexity in some places. The new inverter introduced by team last year has allowed us to redesign our pre-charge from a constant current source to just a few PTC thermistors in series, reducing complexity and the amount of parts used. Lastly, within the relay box that sits on top of the battery, we have reduced the total PCB area by 18%, saving us some weight, but also giving us more flexibility in where we put our electric components. For the low voltage hardware, we have been focusing on introducing new sensors and addressing issues brought up by previous year's team. For example, the rear node has received a new temperature sensor, and the BSD has gotten a new upgraded battery power sensing circuit, improving accuracy. For the embedded software, we have extended our test coverage for unit integration and system level tests. We have worked according to the V model for traceability between the requirements of our tests and the actual tests themselves. And we've also applied software practices to allow us to statically validate our code base. Altogether, this allows us to run tests faster and validate them faster before they're put into the car. And that's all for me. Now I would like to bring up Sven from Aerodynamics.
Thank you very much, Lucas. My name is Sven, and along with my colleagues here, I work with the aerodynamics of the car. In shortness, our job is to make sure that the outer surfaces of the car are shaped in such a way that the energy in the airflow around the car is utilized in the most beneficial way. So what is the most beneficial way then? Well, that's heavily dependent on how the car is driven on track. And together with the vehicle dynamics team, we sit down in the beginning of every season to form performance targets for downforce, drag, and aerodynamic balance. These design targets then shape our entire design process. This year, a clear majority of our simulations have been done in a cornering domain. Given the nature of a Formula Student track, like the one you see here, with tight and twisted turns rather than long straights, we believe that this will give us more representative results in trying to understand the performance of our vehicle. Our workflow is highly iterative, and we start by generating a geometry in CAD. We then simulate that geometry in CFD and analyze the results. If we deem it necessary, we then change the geometry based on the results from the simulation and do the entire process again. As I implied earlier, our workflow is heavily dependent on the mass flow of air over the car. Less mass flow means less energy to utilize for our aerodynamic components, and therefore less generated downforce. The rules by which we build our car states boundary boxes, this one, in which we are allowed to put aerodynamic surfaces. The biggest design challenge this season has been to adapt the aerodynamic package to an update of these rules, which has reduced the maximum height of the rear wing by 100 millimeters. This is the boundary box in the frontal view of for the 2025 season. And this is the boundary box for our season. You might notice the subtle change on the rear wing boundary box, and it is very subtle. But we have to keep in mind that the aerodynamic package of the car works as a system, where all aerodynamic devices are heavily dependent on each other. So the flow from, say, for example, the front wing heavily impacts the maximum performance and the flow to the rear wing, and so on. These new boundary boxes, along with our recent focus on cornering, has had implications on all of our major aerodynamic devices. I would now like to walk you through all of them. This is the new front wing. We have a way less aggressive concept implemented this year, and the flaps have been shaped to let more air through. All in all, this means that less energy is extracted locally and made available for the other components to utilize. Moving on to the side wing, the expansion ratio has been altered, and we have implemented the concept with a single flap. This once again shifts the point of performance extraction downstream. Looking at the diffuser, the geometry has been adapted to fit the new rear wing, as the suction from the rear wing heavily impacts the performance of the diffuser. Additionally, some new underbody strakes have been implemented to optimize the part for cornering. Finally, the rear wing has been moved down to comply with the new regulations, and the geometry has been adjusted for that. We have also implemented some new we have also been implementing some new end plates, which widens the capturing area of the rear wing. That somewhat compensates for the reduced flow area imposed by the rules. All in all, this gives Astrid a CLA of 5.3 in cornering, which is an increase of 15.3% compared to last year. It has a CDA of 1.7 in cornering, which is an increase of 2.5%, and finally a longitudinal balance of 52% rearwards. That's all for me. Thank you very much for listening. I will now hand you over to Niraj, who will talk about the chassis of the car.
Thank you, Sven. I'm Neeraj, and along with these wonderful people, we are the chassis and ergonomics subgroup. The chassis is the foundation of the car. It is the component which every other subgroup attaches to, and it is what gives us a running car. So the chassis consists of the monocoque and the safety features like the roll hoop and the firewall, and ergonomic components like the seat and shoulder padding. Now, this year, our monocoque has the same geometry with a few changes, but the major difference is in the layups. Now, with the new fibers, we are able. So, the chassis consists of aluminum core along with carbon fiber layers. And with the new fibers, we have higher tensile modules and higher bending stiffness, which gives us a lighter panel than last year. So, this results in an overall weight reduction of 12%. Along with the fibers, we also test our panels to the extreme so that they can handle all load cases. So, and we also run a torsional test to see how the vehicle will perform for vehicle dynamics. And now I'll hand over to Sana to talk about safety and ergonomics.
Hello, I'm Sana, and I'm the main person responsible for ergonomics of the car this year. Safety is an important aspect for us in Chalmers Formula Student team. While speed is a goal, safety acts as an essential element in the design process. The notable changes this year have been the roll hoops. We have a new design, and this new design ensures the safety of the drivers in the worst case scenarios. We also have a lighter firewall layup, which saves up to 30% of the weight, while still guaranteeing the same level of security. We have 4 new drivers this year, which means that we have to reevaluate and redesign every part of the car to make sure that they are rule compliant, they fit into the car, as well as they're suitable for each one of the drivers. The parts affected by this can be seen in this picture, all the way from the foot pedals up to the headrest. This design process has been led by data-driven design, as well as multiple iteration design processes. The data that we have gathered has come from the tests from the car, the ergonomic jig, as well as the CAD simulations. We have put the drivers in the middle of the process, the center of the process, so they can give us direct feedback. So we can ensure that the data and the changes that we make to the car are directly affecting them and their performance behind the wheel. And with that, I would like to thank you all for listening to Chassis and Ergonomics, and hand it over to Eric in the control subgroup.
Thank you so much, Sana. Hello, everyone. My name is Eric, and I, together with these two people, are a part of the control group. So now that you've heard of all of the improvements to both the mechanical and the electrical part of the car, well, how do we utilize all of this performance? Well, for that, we need a control system. Our control system is divided into 3 parts. The first part describes how we pick up sensor data from different parts of the car. For example, the wheel speed sensors on the wheels, or the voltages in the T-sack, or, for example, the steering angle. In the first step here, in the signal sensor processing, we filter these signals such that we are able to use them later on in the system. In the second part, the estimations. Here we take these signals and estimate key vehicle signals, which helps us describe how the car behaves in real time. This is useful for the third stage in the control system, which is the control part. Here we have three major control systems. The power control, the torque vectoring, and the traction control. And I will now be talking a little bit more about the torque vectoring of the car. As you may know, in a regular car where you have one powertrain, then to split the torque between all of the different tires, you will have to use a mechanical differential. But this is not the case for our car. We have 4 individual hub motors, which means that we can request torque specifically for each wheel independently, meaning that we can optimize traction in corners by giving each wheel a different torque request. But what's the addition to this year's control system? Well, this year we're adding a ground speed sensor from Sensoronic Solutions. This means that we will be able to measure the ground speed directly instead of estimating it using sensor data from especially the wheel speeds. But how does this improve our performance of the car? Well, a test we did last December shows that running with the ground speed sensor allows us to run at a much higher slip ratio than when running with the old EKF without the risk of wheel spin, which will increase our traction and therefore improve our performance in especially acceleration. Except for this, in control, we have also improved our power control system, which will predict us to give 5% more power in acceleration while still keeping it legal. And we have also decreased the simulation time by at least 75% by making it run in parallel, such that we can run multiple simulations at once. And currently we're working on improved KPIs for the testing season, meaning that we can run more data-driven decisions together with the drivers, such that hopefully we will have a better testing season. Thank you. That's all for me, and I will now leave it up to Jacob in suspension.
Yes, thank you for that, Eric. My name is Jacob, and this is my team members in the suspension subgroup, along with Hanna, Oskar, and Viggo. Yes, so here is our suspension system in this year's car, which is overall very similar to last year's. So to start with, here in the front, we will still be using the direct actuation setup with the dampers in line with the push rod, like this. And also we will keep the 2 different damper mounting points here in this mount here, which ensure a well-balanced car both in autonomous driving and in manual driving. And moving over to the rear, we will also use the same overall concept, but the position of the anti-roll bar has been moved forward, which makes it possible to combine the mountings with the mountings of the rear dampers. And this is a change that both reduces the weight of the system, but also reduces the inertia of the car, because now we have more mass towards the middle. Yes, and new for this year are the rims. So the rims will be 1 inch wider this year, increasing from 7 inches to 8 inches. And test data has given that this increase will give us a performance improvement of at least 3.5% in lap time. And this is mainly due to the better sidewall support for the tire that we get with the new wider rims. And also worth mentioning with this test is that the test was done with aluminum rims, but we are currently in the manufacturing process of making the new carbon fiber rims, from which we expect an even higher performance increase, because they are both stiffer and lighter compared to last year's 7-inch carbon fiber rims. Moving over to the wheel assembly or the wheel package, a lot of the overall concept will be kept, but a lot of design work has gone into redesigning and repackaging with respect to our new wider rims. and also trying to shave down those extra grams of unsprung mass. Moving over to the steering of the car, new for this year is our in-house developed steering rack. So by using a titanium steering rack and pinion, we now see an increase in stiffness of 60%. And also designing it after our exact needs, we have been able to significantly increase or significantly reduce the backlash or the play between the gears in the rack, as well as reducing the overall weight of the steering system. Also regarding the steering, some updated suspension attachment points combined with an adjusted steering ratio will give us a reduced steering effort required by the driver. So in this year's car we will have a steering effort that's reduced by 35%, which makes the car much more drivable and will give us a better performance on track, and especially in endurance. Furthermore, the pedal box have been improved by a weight reduction of 18%, as well as a new accelerator pedal position sensor which will be used, which allows us to increase the adjustability of the accelerator pedal by 25%. And last but not least, the brake discs has been further optimized to be able to make it 23% lighter compared to last year's. So with that being said, we now head over to Benjamin and to the autonomous system of the car.
Thank you, Jacob. I am Benjamin. These are my teammates, and we are the autonomous subgroup, who are responsible for the hardware and software which Astrid needs to run without a driver. First, I will give a general overview of how the autonomous system works, and then I will talk a bit about what we have worked on this year. The first part of autonomous driving is object detection. In our case, the objects that we are trying to detect are the cones which delineate the racetrack. We use a LiDAR sensor, which you can see in the left diagram, which provides us with a collection of points which describes the environment around the race car. An example of such a collection of points you can see on the right diagram. And so how do we extract the cones from this collection of points? Well, first we need to motion compensate the sensor outputs and then remove the points which represent the ground. Then we use clustering algorithms and some knowledge on the geometry of the cones to determine which of these remaining cones are actually, which of these points actually represent cones. Once we have these cones, we can start trying to build a map of the racetrack. But just having a map of the racetrack is not very useful if you don't know where the car is within that map. So we are using a simultaneous localization and mapping algorithm in which we take not only the detected cones, but also some velocity estimates of the car to calculate the most likely map of the racetrack as well as the position of the car. Once we have the map and the position of the car, we can start trying to find the optimal race line. On the right diagram, you can see a top-down view of the map constructed by the mapping algorithm, where the yellow dots represent cones and the green box is the position of the car. And so what we try to do is find the limits of the track, so its sidelines, and also the center line. But the center line most of the time is not the fastest race line, so we optimize this race line by taking into account attributes such as curvature, which will result in the following red race line. But knowing this race line will not get the car to drive. This is where we need a control system. The control system takes the calculated path and tries to determine the torque we need to send to the motors as well as the steering angle to have the car actually follow the race line. If we combine all of this together, we get an autonomously driving car. Our autonomous system is already very performant, which is why we need a very good argumentation if we want to make new design decisions. This is why this year we have spent a lot of time working on developing performance indicators which help us measure how well each component of our autonomous system works. To complement these performance indicators, we have also created an automated test system which helps us collect and store data, which we can then later use to analyze and synthesize information and validate new design decisions. Regarding some improved performance metrics for this year, on one hand, the automated test system saves us a lot of time. Previously, we would have to spend around 5 minutes to just set up and run a single test. The automated test system allows you to run 10 to 15 tests in the same time without having to do any manual setup. Additionally, we're also working on an adaptive velocity planner, which, according to a test we did in December, allows us to shave off up to 3 seconds on laps during track drive. Finally, we're also trying to tune the frequency at which we want to run our LiDAR. By decreasing the frequency, we could get more points in our collection of points, which could in turn help us detect cones farther away, create a map of the track faster, which then in turn could help the path planning algorithm as well as the control system to tell the car more accurately what it has to do. This is everything from the control group, and I'm inviting Oscar to give some last words before finishing. Thank you.